So now we're going to look at applications of triple integrals. And the one application we'll look at is in computing the center of mass. Okay, and so in computing the center of mass, we're going to be computing the mass of an object by integrating a mass density over the solid region, and then by computing these moments about the three coordinate planes. Okay, so the equations that we'll need are the following. So we'll need an equation for computing mass, and as I said, to compute mass we can integrate over some region E the density, or mass density, which is rho of x, y, z, dv. Okay, so this is a triple integral that we would convert to an iterated integral. And now there's moments about the three coordinate planes as well. So moments about the coordinate planes go by the following formulas. So the moment about the yz plane is a triple integral where the integrand is x times density. And so if we write down the moment about the xz plane, this integral is going to be a triple integral where the integrand is y times density. And then finally the moment about the xy plane, we are going to do a triple integral of z times density. And all three of these integrals are over the region, solid region E. Having computed these quantities, the center of mass is going to be given by, so the center of mass, which we will call x bar, y bar, z bar, is going to equal, well, x bar is the moment about the yz plane, and then divided by the mass m. The coordinate for y, the y coordinate is going to be the moment about the xz plane divided by m, and the z coordinate is the moment about the xy plane divided by mass m. Okay, so the example we're going to do is we're going to find the center of mass of a solid of constant density that is bounded by the parabolic cylinder x equals y squared and the planes x equals z, z equals 0, and x equals 1. Okay, and so first thing to compute is mass. So we're going to have mass equal to, we're going to set up an iterated integral where the density is constant, and we're going to integrate first with respect to z. Now if you notice, if we're going to integrate with respect to z, we have to find surfaces that are bounds for this region. And if you look, we do have two equations for z given as functions of x and y. And so those equations are z equals 0 and z equals x. I mean, I have it written x equals z, but that's also z equals x. So on the inside, we are going to integrate from z equals 0 to z equals x. And we will integrate rho, where rho is a constant, dz. And I'm going to choose to integrate the order dx, dy. Okay, and the reason is because if we draw the region that we get if we project the solid region onto the xy plane, we get the following picture. So this is the y-axis, and this is our x-axis. And if we project the solid region onto the xy plane, notice we have the parabola, sideways parabola, x equals y squared, and we have this line x equals 1 that form boundaries for so I'm just going to draw an arrow from x equals y squared to the curve x equals y squared. This is the region that we are going to integrate over once we do the inside integral. So, and the inside integral is already set up with the limits of integration, 0 and x. And so now if we look at that region and construct an iterated integral based on a double integral, well, we're thinking of it as a type 2 region. Okay, we have a, thinking from left to right, we're going to integrate with respect to x before we integrate with respect to y. So the curve that is a bound below, that is a function of y, is y squared. And the curve that is a bound above, that is a function of y, is the constant 1. Okay. And now y, what does y range from? Well, hopefully you see from this region that it ranges between -1 and 1. So limits on the outside are -1 and 1. And in computing this integral, antiderivative of on the inside is rho z, and then if we plug in x and 0, we end up with simply rho times x, and then we integrate dx dy, and then this equals integral from -1 to 1. Antiderivative here is rho over 2 x squared. Limits of integration are y squared and 1 dy. And if we plug 1 in, so we have a constant of rho over 2 outside in front of the integral, and then integrate from -1 to 1. Plugging in 1, we get a 1, and then minus a y to the 4th power dy. And from here, I will ask that you check that this turns out to be 4 rho over 5. Alright, our moment about the yz plane. We are integrating from -1 to 1, and then integrating from y squared to 1, integrating from 0 to x, x rho dz dx dy. And so this is going to equal, well, the antiderivative with respect to z is z. Plugging in x and 0, we end up with an x squared rho, or rho x squared, dx dy. And this is going to equal an integral from -1 to 1. And our antiderivative in this case is rho over 3 x cubed. Limits of integration are y squared and 1. And so I'm going to move the rho over 3 out in front. Integral from -1 to 1. We plug in 1, we get a 1. 1 cubed is 1, and then minus y squared cubed is y to the 6th power dy. And I will ask for you to check that this value is 4 rho over 7. And to compute m xy, we are going to integrate from -1 to 1, integrate y squared to 1, integrate from 0 to x, z rho dz dx dy. This is going to equal integral from -1 to 1, integral y squared to 1. Antiderivative now is 1/2 z squared rho, and if we substitute x in, we will get a rho over 2 x squared. Of course, when we plug in 0, we get nothing, and so this is our integral, and then we have dx dy. Now when we integrate with respect to x, I'm going to move out coefficients in front, so we're going to end up dividing by 3, so we're going to have a rho over 6 integral -1 to 1 x cubed, limits of integration are y squared and 1, and this is going to equal, this is integral with respect to y on the outside, rho over 6 integral from -1 to 1 of a 1 minus y to the 6th dy, and I will ask for you to check that this is 2 rho over 7. The computation of the moment about the xz plane, it turns out that it's going to equal 0. Now we can do that by computing a triple integral of y times rho, but from symmetry it turns out that this moment is going to be 0. And so our center of mass, which is our x bar, y bar, z bar, equals x bar is the moment about the yz plane divided by the mass. So we got, for the moment about the yz plane, we got 4 rho over 7, and then the mass was 4 rho over 5. Okay. Our y coordinate, well, since our moment about the xz plane is 0, it's 0. And then coordinate, the z coordinate for the center of mass is a moment about the xy plane, which is 2 rho over 7. And then, of course, divided by the mass, which is 4 rho over 5. And in simplifying, this equals 5/7, 0, 5/14. So this is our center of mass.